The Loads tab in the wrap gives us a place where we can define the loads that are applied to our joint. Now, if I just take you down to the areas where we define the loads, we can define a joint tension and a joint shear load here. And to kind of bring everything together, I'll use this chart to show how it ties in with other aspects of a bolted joint that we've already discussed. So we've mentioned already how we have a high preload bolt in a batch of bolts, which is the highest preloaded bolt, and then we also have in the same batch, the same tightening method, we would also have a low preload bolt. So these two data sets represents the extremes of pretension variation that we get in our bolts. And we've also seen, so the red lines defines the preloads before any loads are applied, that the preload and in fact the clamping force will be the same. We can see that this is less because this is the lowest in the batch, that's the highest in the batch. Now as soon as we apply a tension, some of the tension increases the bolt load, but more of it goes into decreasing the clamping force. And I think we've seen this already by reference to the chart on the tightening tab, which is there. So what we have for the highest preloaded bolt is the initial preload, the final tension once the tension load to the joint is applied, and the remaining clamp force. But of course what we're actually worried about is this lower preload will also have a lower clamping force, and we require the clamping force to be present if we're to sustain a shear force. So if I just make that a bit clearer, we can see in the joint shear area we have a certain coefficient of friction, and we rely on that coefficient of friction together with the clamping force to provide a load path for our shear load that's applied to the joint. Now in this case everything's okay. So in fact, and I can show you by reference to the same graph here, we have this is the highest amount of clamping force we have, that's the lowest amount of clamping force we have in the batch, and this is the required clamping we require. So in both instances, if that's how much clamping force we need to sustain that shear load, then we're very happy because we have it in the low end of our batch, and we also have it in the, obviously, in our higher end of the batch. So let me just take you down and let's play a few tunes with this. Let's increase this load here. There's two ways of defining this load. We can set a user defined load as in here, so I'll set that now to 5,000, or we could have in fact also defined it as a percentage of the bolt shear load as well. But for now, we've increased this from 1,000 to 5,000, and in fact when I go back up to the graph, the required clamping force I need to sustain that shear force has now increased. And in fact, the required amount of clamping force is greater than the amount of clamping force that's available in the lowest pretensioned bolt in the batch. So in fact, what this means is that any bolt behaving or looking toward at the lower end of the batch will fail. At the higher end of the pretension spread, this would pass, but we can't guarantee that every bolt is going to carry this load at the moment. So I hope you can see here that there's ways of defining the joint tension and the joint shear load, and if we always come down to our conclusion here at the end, this in fact the conclusion here is that the joint would slip under the shear load, and as soon as a joint's slipping there's the potential there for vibrational loosening and all kinds of other problems.